Yeah.
So today we will be discussing the two very important supervised learning algorithms, perceptron and support vector machines. The underlying assumption with both of these algorithms is they assume that the data is linearly separable. So that means you can kind of divide the data, like the output, into two categories. Either it's going to be positive or it's going to be negative. Okay, so we'll first start with perceptron. So the concept of perceptron comes from neurons. So this is like a human brain neuron, and just to give the basic idea, everyone knows about this. This is your cell body. Then there is an axon through which the signals that we call spike trains reaches synapses, and with synapses, the other neurons are connected. So this is how the information is propagated from one neuron to another neuron and finally converted into muscle actions. Okay, so if we kind of change this, like that diagram, that neuron diagram, into an artificial neural network. So what we have is, this is our neural body. These are the different signals that we are getting. So let's say we have three signals. These are my input vectors, x1, x2, x3. Each of them is assigned some weight value. And let's say theta is your threshold. Then y is your output. That means what should be the spike trains after that, like what should be the outcome after this neuron processes the information. So we can say that that will be the summation of all these inner products of xi into wi. Okay, so that is basically your activation. This is how you calculate the output vector y. And then there is a firing threshold. So this basically decides whether your data lies in the positive category or the negative category. If this is greater than 0, then it's 1, that means positive, and if it is less than 0, then it's 0, it's negative. So this is the very simplistic form of the neural networks, or like the basic building blocks of deep learning. And I think this algorithm came in early 1950s, and so yeah, perceptrons is like the building block of, let's say, deep learning and all that. And yeah, so the two assumptions that we make for this algorithm to work is the binary classification and the data is linearly separable. That means we assume we can divide all the data points in the training data set into two categories. We say it's an online algorithm for calculating that linear threshold function. Why we say it online algorithm? A machine learning algorithm is called online when you are processing each point one by one. Okay, so how basically this algorithm works is like, let's say we have a weight vector which we are assigning to each input data set, initialize it to 0. That means we are assuming every data point is misclassified. So that means all positive points are initially classified as negative and the negative points are classified as positive. And while true, we will assume this m is the number of the count of mistakes that the algorithm is going to make. And for each data point x, y, and d, what we are going to do is, like, we are going to see that w into x, right? I said, like, the summation of w into x is equal to y. If it is less than 0, that means my point is misclassified. Okay, so I will update the weight vector. And the weight vector is updated by w plus the initial value of w into the product of y into x, and I will increase the mistake count by 1. And the moment, like, if, like, in our algorithm, like, w is predicted fine, so in that case m will be 0. So we will keep on continuing this till the time we have mistakes is equal to 0. So what is happening in perceptron algorithm is, like, you keep on updating the weight assigned to the input vectors till that w is kind of differentiating the points into two categories. So it's gonna be more like, you have markup. So let's say this is my plane where I'm considering the data points are there. So these are the two categories. This is my W vector.
We can move to that side.
Trip.
Can we move to that side?
We can.
Okay.
Oh, thank you.
So this is my W vector, my threshold function. And in the case of perceptron algorithm, I assume it's some kind of hyperplane. Why we say it's hyperplane? Because right now we are considering the points are in the two-dimensional space. But these points are what? My input vectors. They can be in three-dimensional space, four-dimensional space, or anything. So we say it's a hyperplane. So in whatever dimension it exists, it's going to divide the point into two categories. Okay? So as we studied in regression and every linear separable model, your modeling equation for the threshold function is, everyone remembers this clearly? Yeah. Right? So what is this? This is your input vector, your training set. That's going to be your points like x1, so on to xn. Then you have a weight vector, how much weight you are assigning to each data point. Let's say W1, W2, W3, so on. And this is some bias value. You add this bias so that your plane moves away from the origin. Okay? So this is your threshold function. And what we are doing in perceptron algorithm is, let's say we started with like every point is misclassified. We keep on updating this W value. So it might, in the first scenario, let's say W is over here. Okay, we keep on adding, like if you say if it's misclassified, we keep on adding W is equal to W plus by X. That means we keep on moving this plane till the time we think the solution is optimal. Like this is the hyperplane that is clearly dividing the data sets. So the next question comes is like how we are going to decide like our algorithm have converged. How we are going to say that this is the optimal solution. Okay.
And how to select bias value?
How to select what?
Bias value. Bias.
Bias value. So bias value is again experimental. Like you hit and trial method, like how you're gonna classify this. So this is more like how you add a constant C in a linear equation. So that you have to see. Okay. There is no rule to or like no mathematical formula you can deduce the bias value.
So choosing the wrong bias, the learning algorithm will not converge,
yes.
Right? And you can
as
get into infinite loop.
Last lecture we saw that error is the combination of bias, variance, and noise. So we always want the bias to be low. You remember, like when I was talking about the model selection, there is an optimal point, that value of bias and variance. Like it should be low bias and high variance. So that combination we need to maintain.
If you go back to the previous function, when you said start with everything as misclassified,
yes.
What does that mean? Start
So,
with everything.
Let's say these are my data points, and let's say this is my W vector. I'm assuming all these points are positive, lying to the positive side of this weight vector. And let's say all these points by default are negative. So I'm assuming that every point is misclassified.
But that may not actually be true.
That may not actually be true. And then we keep on moving these points. like this weight vector. So let's say first, after the first update, it comes here. Then after the next update, the hyperplane moves over here. Then after the next update, the hyperplane moves over here.
So W equal to 0 is the starting point, or is that what you're calling is misclassifies everything?
W is equal to 0 is the starting point.
But that does not necessarily mean that it misclassifies everything.
It may be few points, maybe not.
If W equal to 0 is the vector,
If that is going to be the vector, so
then it will actually not misclassify anything. In the first
it won't
instance itself, it will
misclassify
come to
anything.
M equal to 0.
Yeah. I start with the assumption that everything is
Your
misclassified.
assumption, okay.
And if it is not misclassified, this mistake will come 0. Like this y into wtx, if it is greater than 0, that means everything is classified properly. That means there is no mistake. W is equal to 0 is the solution.
Yeah.
Okay. Then few points about this perceptron algorithm. It's a supervised learning technique. It's a single layer feed-forward neural network. We'll talk more about this feed-forward later on. And so basically in this, the data sets is being differentiated into two categories. And we iteratively learn the weights over here to find the solution to this kind of linearly separate the data. Okay.
So how does this solution tend towards the optimal?
Yeah, that's what I'm going to talk next. So the basic thing is like there is a concept or like the basic intuition is let's say this is the hyperplane value I calculated. Okay, and these are the points. So how will I know that this is the right solution? So the basic assumption or while deciding that is, or the intuition behind is the difficult points. Like let's say over here. Not that close. Okay. So these are the points which are going to classify or like kind of help me decide the which is the optimal hyperplane value. There is this hyperplane, then there is this hyperplane, and then there is this hyperplane. Let's say with perceptron we have three possible solutions. Okay. So what I do is from all these difficult points, this is the shortcoming of kind of perceptron algorithm, and then from there this support vector machines comes into picture. So we say these difficult points as my support vectors. Okay, and I calculate the distance from these support vectors to the hyperplane. Let's say this distance. Let's say this distance. Okay. Similarly for the case of positive points and negative points. Okay. Then the basic idea behind selecting the optimal hyperplane is maximum margin.
So that means you've already gone into support vector.
There is no kind of way to predict that this is the best algorithm or the best outcome from the perceptron.
So perceptron gives you an arbitrarily
Set of optimal solutions.
okay.
And there is one important point about that is with the perceptron algorithm, we have mathematically proven it. The maximum number of mistakes that you can do is 1 upon gamma square, where gamma is your basically this distance between the classifiers. These points, the difficult points, and the distance between them from the hyperplane. So this is like if you see online, you will see the proofs and everything. So that's the maximum number of mistakes a perceptron algorithm is going to make. And again, when we talk about like convergence, so if the data is not linearly possible, there is no way perceptron algorithm is going to give you any solution. Learning will absolutely fail. But in the case when the training set is linearly separable, so perceptron is guaranteed to converge, and there is an upper bound on the number of times how we need to kind of adjust my weight vector. So that can be controlled by that 1 upon gamma square. Like that's the at most number of mistakes the perceptron algorithm is gonna make.
Can we use the corollary to decide that if the perceptron fails to converge, it means that data is not linearly separable.
So the algorithm
No,
will just
we
run
can't.
for a long time. How do we decide it's case 1? Or it's just slow?
So actually, when I say it's a supervised learning algorithm, you somehow know information about the data points. Like you won't apply it on a random data set. That's one assumption.
But can't
like
perceptron return best optimum that they can find out, right? Suppose it's not it's a linear separate, right? But there could be some error in the sense like
So the
some
error
data
value
in
would
the
be-
rep
see,
could be underlined, right? But
the thing
optimal.
is, with machine learning algorithm, you can possibly apply all these algorithms on any kind of data set. Then again, whether that model is going to work for your data set or not depends on how much the cost function and the error values are coming up to. Like I can go ahead and kind of modify the the unsupervised data or the unlabeled data and kind of apply the labeled data algorithms on that and kind of find out some solution that's best for that problem. But that might not be the right approach or might not be the right way to properly classify or predict the value. So answer to that is difficult, but I don't think so we can clearly say that if the perceptron is failing to converge,
It's not linear. Got it.
it's
You
very
can't say
possible
that.
it's not a linear problem, but we can't guarantee that.
Okay.
Okay, so this is about perceptron algorithm. You guys should look ahead and like see. It's a very simple mathematical proof how we say that the at most number of mistakes made by the perceptron algorithm is 1 upon gamma square, where gamma is the margin distance. So the distance between your hyperplane to those difficult points which are kind of difficult to classify. Okay, so yeah, that is the problem with the linear separators. Like let's say all these are the calculated hyperplane values, how we are going to decide which is the optimal one. So from there, this the support vector machines comes into picture. So it helps in kind of finding out of these all possible hyperplanes, like let's say A, B, C, which one is the best hyperplane to kind of classify the data. And as I said, the support vector machines. So the support vectors over here are these difficult points which are closest to the hyperplane. Okay, those are my support vectors. And the notion is to maximize the distance between the hyperplane and these difficult points. Okay? Yeah, that's it. So this is the mathematical formula, how we are going to calculate the distance. And so let's say this is your hyperplane value and these are your support vectors. So this R is basically this value, how to calculate the distance between any point to the hyperplane. Okay, and if this is my hyperplane and this rho is basically my maximum margin. Understood? Anyone have any question?
You mentioned something about choosing the support vectors as the nearest points to the plane. Why and how many points do you choose instead of taking the whole set? Why can't I use the whole set to calculate the support?
If you use the whole set, it's unnecessary number of computation. The intuition behind this algorithm is the uncertainty in or like the chances of misclassification are going to happen near the decision boundary. The points which are clearly classified, like the farthest point, if it's classified as a negative point, there is very less probability that it's going to be misclassified.
Okay.
These are these points where kind of hyperplane is like very dividing or the misclassification rate is high.
So fundamentally,
it's based on this intuition, like
yes,
how we are
yes,
going to
so it's simplifying the computation.
computation over there.
But then how many?
So there is one more thing except computation. So why it goes support vectors? So the support vector thing is like, so let's say you want to do classification and you have a lot of data points. So it's not that every data point will give you the correct information to classify it in a way that is linearly separable. So you have to neglect some of the outliers and you have to build your classifier on top of the good examples. Okay? So that's what support vector does. So it tries to get a vector based on the good examples and try to neglect your negative examples. And that's what we call support vector, because it's based on those vectors.
What do you mean by good examples?
So good examples means let's say I have a classifier. So, so she was drawing this, there was a diagram and where you see all the points. So it's not like that all the points are very well linearly separable. So maybe you need to reject some of the outliers which are anyway not gonna be classified correctly. So let's say some data points give me very nice features, and on those features they fit very well. So I need to first identify those data points which fit on those features, right?
Okay.
Yeah. So based on that, so those are the good examples for me. So let's say you gave me so many data points. Let's say you gave me 1 million data points, and I will try to find out first 1,000 or let's say 10,000 data points, and based on those 10,000 data points, I can get at maximum information so that I can plot my vector to do the data linearly separable.
All right.
Okay.
Yeah.
So then the idea behind how we decide the optimal solution is like we kind of maximize this margin, and that is based on the intuition, and there's some pack theory that says that, and so we can kind of say that in deciding the optimal solution, like out of the possible all hyperplane values, the final decision is based on the support vectors. The rest of the data points are kind of ignored. And yeah, that's what is SVM. This is a neat slide. Okay. What?
So other thing support vector, it hardly gets the overfitting or underfitting because it doesn't get affected from your negative example.
Okay.
Yeah.
So yeah, these are some of the other points. In SVM, what we do is like we maximize this margin around the separating hyperplane. The decision function is fully based on the support vectors. Mathematically, it's a quadratic programming problem, and more used a lot in text classification techniques. And this is kind of like mathematically, let's say W is my decision boundary, my hyperplane vector, X is my input data points, and Yi is my output vector, that is basically my classification value plus 1 or minus 1. So again, as we saw in the perceptron, the function of xi, that means my output is going to be the signum value of the wtxi plus yt. So either it will be positive or negative. If this value is greater than 0, it's going to be a positive point, and if it's less than 0, it's going to be a negative point. And the thing, or like the kind of mathematically reduced is like usually this functional margin of the data set is twice the minimum of the functional margin for any point. Again, there are proofs to prove that. Whoever is interested can look into that, and I can explain that. So yeah, this is again. Do you guys want me to go into the mathematics or? So what we are doing is for each data point, okay. So how we find out this R, okay? How we say that is that WTX plus B divided by mod of W. How we kind of calculate that. So let's say this line x to x dash. Okay, this is gonna be a perpendicular decision boundary, and this is gonna be parallel to my hyperplane value. Okay. So the unit vector across this line is going to be W divided by mod of W, and if we calculate to try this x dash, that's going to be this. Okay, and since it's like this x dash is going to be parallel to my hyperplane, it's it's gonna satisfy this equation too. That's this hyperplane equation. Okay. So, and we know that like mod of W can be written as the square root of this also. So we just kind of substitute these values over here to calculate the distance up. So that's how we calculate the distance between any data point to the hyperplane. Okay, and the SVM is basically to kind of maximize this margin. So margin is what? The distance between the support vectors and the hyperplane. So this R formula we can use to calculate the distance between the support vectors to the hyperplane, and then we can take the derivative of that to find out the maximum value of that row. So for the hyperplane where the row is maximum, that is my decision boundary or the final decision boundary or the optimal solution for this kind for the given data set. Okay.
And go back to the last statement which was made in the fact the function margin. Does this also explain this?
No, for that.
The price
there's
of
a
minimum,
separate
that's different.
definition.
Okay.
Okay. And then again I'm repeating this. So basically the point will be classified as positive. So there are cases where you take it as 0 or -1. That just basically depends on where you are putting your origin at. Okay. And yeah, again the the distance calculation between any point to the hyperplane is this formula, and the margin is twice upon mod of W. That's how you calculate, or the maximum, like the margin value. Okay. So, yeah, I think over here what I wanted to tell is, okay. Now there are variants of support vector machines in the case where we want the data is not linearly separable, or like few of the data points or something like that. Like we are not satisfying our basic assumption. So in that case, what we need to do is, okay, all these are mathematical slides basically where how you kind of optimize this into a quadratic problem and kind of find out the solution, the better formulation of this, or like all these things. Have a look at this. If you guys find any difficulty in understanding this, I will explain it later on. And just to keep it moving, because we got the getaway from the SVMs, right? Like the maximum margin and how we calculate that distance, right? So there are better solutions how we can predict this phi better, and all those things are there. And yeah, this is again one thing. I've just added these slides to kind of give it a completion. So then comes the category like when the data is not linearly separated. So in that case, we call it soft margin classification. We kind of add some slack variables to allow misclassification. Okay. So the idea behind is like we should allow some errors, let some points move to where they belong at a cost. So and still we kind of, the intuition remains the same, that we want to maximize the margin. We want to, but we are adding some slack variables. Like let's say these are my slack variables. These are not my support vectors, but I added these 2 points in the calculation of this maximum margin. So that means you are taking some misclassified points or like some few extra variables in your calculation.
No, so these variables existed or you have introduced them?
These are like data points. These existed.
These existed.
These existed. But these are not necessarily
How do you choose them?
The support vectors or the slack variables.
The slack variables.
The slack variables basically there are various methods like
Because to come to a slack variable, you have to first assume a hyperplane on which they have been misclassified.
so you will have the hyperplane, right? You will have, let's say, 10 hyperplanes. Okay, and based on the 10 hyperplanes, you'll get different support vectors, right?
Okay.
And they might not be same. There will be few points which are coming again and again in the case of hyperplane, but they might not be the support vectors. So you take them as slack variables. So that means you are widening the margin of your classifier. You are like allowing it to make more mistakes. Understood? So it's more like, let's say, so when you mathematically or like in MATLAB, my MATLAB broke. I will show you the tutorial in the next few days. So when you will see these algorithms, I think you will understand it better. So let's say I will show you moving, like let's say the first hyperplane comes as this. Let's say the first hyperplane comes like this. Then I update W, it comes like this. Now in this case, support vector is this point or this point. Okay. Then it moves. Then the support vector is this point, this point, this point, this point. Okay. Then it moves. Now I see the points are getting classified more accurately. This is the support vector, this is the support vector, this is the support vector. Let's say I take these 2 points also over here as my slack variables. So
I don't understand what you mean by that. These 2 points also over here as my slack variables, or were there 2 other points?
These are the existing data points, but these are not the support vectors to these hyperplane.
Okay.
This newly computed hyperplane, this is not the support vector to these. Okay. The support vectors to these is these 2 points.
Yeah.
Okay. Now I'm adding a slack. Let's say take from the previous hyperplane, which was kind of classifying the data accurately. Take 1 or 2 variables from there, or maybe all
Accurately,
more or less accurately. Okay, because I'm trying to find the optimal solution.
Okay.
There might be at this much distance also 2 hyperplanes. I'm gonna decide these 2 out of these 2 which is the correct one. And maybe with this, let's say there is one more the input data point is there, that can be taken as a slack variable. Okay, so then the idea behind is based on these slack variables and my support vectors, I find a new optimal hyperplane. I modify my weight value.
So what is the role of these slack variables in an equation? Is it just ignoring them, or is it more?
It's not ignoring them, it's taking them into calculation. That means you are kind of widening your hyperplane even more than that 2 upon mod W.
So they will have a negative distance, right? I mean, how does
They
that
are
work?
negatively, they are reducing the accuracy of your support vector machine. But we are allowing them maybe when the data is not linearly separable.
What does it mean by factoring them in the equation? You will use them as support vectors?
Yes.
Okay, so in that calculation of the summation, they will contribute negatively.
Negative. Yes.
And which means you are letting your support vector drift towards the misclassified things? Oh, no, not the misclassified, the
Calculate, kind of factor in those misclassified points.
yeah. But
You are
isn't that
allowing
what
it to make errors.
Okay.
And we are doing this so that in the case when the data is not linearly separable, we are factoring in those noises or like the erroneous classification values. So that's why it's called soft margin. We are not strictly cohering with the definition of the support vectors.
Okay. But so it's not, I mean, initially I was thinking it's something to do with ignoring these points, but it's not actually ignoring these
It's not
points.
ignoring, it's including them in
It's
the
actually
calculation and kind of
incorporating
negative, yeah.
Because if you took strictly the support vectors as the neighborhood points, you're still having misclassifications. That's why you introduce the
Misclassification so that I improve my hyperplane.
Okay, but you will never get to a perfect hyperplane because
It won't be
not
perfect
linear. So then at what point do you decide that it is enough?
Depends on how much accuracy I want to achieve and how much I can achieve based on the data.
Which is accuracy is again defined by minimizing what?
The cost function values like the Euclidean distance or like the Manhattan or the zero error, squared loss errors that I calculate, precision, recall,
Okay.
the
And
bias
taking
and the
these-
variance.
Taking these misclassified points is better over taking the other points. Increasing the width of my support vector to
Yep.
the correct term.
Yes.
Okay.
So that's the variant of the support vector machines. In mostly the real world data examples, really this kind of like the exact or the strict form of support vector machines are used, but they are highly used in text classification techniques. I'm gonna take like in the tutorial, the demo that I'm gonna show, we will work on some cancer data set or something, and I will show you how that works. Again, when you're adding, so how the whole formulation is changing. So basically, if you see, you're adding this summation of these slack variables over there and kind of minimizing. So yeah, those all things are there. And yeah, the one important thing is like when you are doing the summation of these slack variables, the distance between the slack variables and the hyperplane, you add a constant c. So this c is to kind of prevent from overfitting. Again, this value is experimentally reduced. You see hidden trial, like start with different values of c and see how like which hyperplane fits better to your data points. And when I say which data point, which hyperplane fits to your data point, right now I'm making you assume like in a 2D context, but when you're gonna actually apply it on a problem, you're gonna decide it based on the bias, variance values, and the noise error values, all those error functions that we saw last time, and how we are gonna select those optimal point, like the optimal C value where the variance, the bias is high, variance is low. That is why the correct C value. Okay. Again, the soft margin is like not easy to calculate. There are mathematical challenges, how use Lagrange multipliers and all those to solve those problems. These are the mathematics. You can go through them, and if anyone have any questions, let me know. So that is one thing. So again, now you have your decision boundary, how you're gonna classify any test point. So if any test point that is coming, this is my optimal hyperplane value, and if this is my test point, so based on this, these are my negative points, these are my positive points. That's how I'm gonna classify any new test point. Okay. And so this is like a linear SVM. Now there is another variant. So we saw linear SVM, we saw a maximum margin classifier, we saw a soft margin classifier for the case of not so linearly separable data. Now there is a concept of non-linear SVMs. And in non-linear SVMs, we talk about kernelization. So kernelization is basically, let's say, your hyperplane. You kind of divide your data points into small set, and for each kernel you kind of calculate the hyperplane, and then these are all added mathematically to find the final hyperplane. So this is in the case of high dimensional data, when the data is not like 2D, like we can divide it into two categories or something. So there comes the non-linear SVMs. Okay. So this is like the whole kernelization thing. I think I should go that in the next lecture.
Yep.
So the basic idea is like your feature space is not two-dimensional. So how you're gonna divide your linear data or the data set into the phi of x. So this phi of x is your kernels.
So kernel is like transformation of a data.
Transformation of the data from one dimension to another dimension. So let's say this is my linearly separable or one dimension, or like this is the other form of data points. So how I'm gonna, let's say this is my data point. Okay, these are my data points. Is there a way you can think this data can be linearly separable? Any hyperplane which gonna classify them accurately?
No.
No, right? If I change it into a different dimensional space, okay, now I can see this might be a hyperplane that can divide it into two different points. So this transformation is basically kernelization. How you are transforming your data set from some dimensional space to another dimensional space to make it linearly separable. So these are your non-linear SVMs.
But the problem is not about feature space being two-dimensional.
It's about in a different dimensional space. Like basically, if your data is, let's say, not linearly separable in a two-dimensional space or a three-dimensional space, where you can kind of visualize and mathematically do or solve those linear equations, the SVM equations. You transform your data.
But you transform it to another two-dimensional space, right? It's just a transform to another.
No, they transform to 3 dimensions.
3-dimensional, 4-dimensional, depends.
They increase dimension.
And then for each dimension, you're gonna calculate the SVM separately and then kind of merge it to find out the optimal.
So a transformation changes the number of dimensions? No.
It can.
I can keep this transformation on the same number of dimensions, but it's a transformation which.
What kind of transformation?
I don't know. I don't know. Can I do a 2D to 2D transformation such that it will give me a hyperplane?
Normally, that doesn't happen, like because if the data point is linearly separable in one dimension, you will see it. It's normally you have to convert it into a higher dimensional space to kind of
Actually,
solve
you
the problem.
can, right? Suppose like you have the XY plane, you can convert to R theta plane. Basically, you have R theta. So now you conversion to 2 dimension, then you can have linear separable in this case.
In this case itself.
In this
right?
case,
Yes, only in this case. But in different case, you could transform
But
differently.
again, it's a dimensional change, right?
You
But
change
the
the
space is
2D.
it's a 2-dimension.
Yeah, but you just change the height of the plane.
The feature or the
That could be done, but the problem is like, how do we choose the kernel? You have so many kernel, and
There are so many
you can
kernels.
transform to anything.
Yeah.
Then how you know which one is a good?
So there's like the whole kernel trick and how we do that. We'll go that into the next lecture. And meanwhile, I have on the wiki page posted 2 tutorials how you can download Octave. So Octave is just like MATLAB, it's free. You don't need any license or anything. Those are the 2. I'm still not able to kind of do it successfully on my machine because my MATLAB is broken for some reason and I just can't open it. So, but still try to follow those 2 tutorials. It's like very much inclusive of all the steps that you need to do. And I will also kind of download it and post it, like what are the missing things over there. And then we can start working on taking like the sample data set. So there is a machine learning toolbox and all those toolboxes are there on Octave, and there are some sample data sets already there. So we'll start, maybe we can have one workshop where we will start with a data set, start plotting it, how we can plot it into a 2-dimensional space, a 3-dimensional space, and then start calling these functions. Like let's say there is a function for SVM, but I keep on changing the parameter values. Like I keep on changing the let's say the support vectors I'm choosing. So we will see that how the hyperplane is moving. So that will give more clarity. Yeah, I will do that tutorial ASAP. That's it. Any questions? Okay.
So we're going to talk about this next time.
Yeah, my MATLAB is broken. I'm somehow not able to start it. I don't know why. So there is one requirement for X quads. It worked perfectly fine last time. I don't know. I have no idea.
Because you update that.
I didn't update my OS actually. So that should not be the case. And the only requirement that I was seeing on the Stack Overflow is like I need Xcode and Xquads. That both is there on my system, but I tried reinstalling it, still doesn't work. But anyway, I will share those code values, those MATLAB files where these functions are there, like the SVM and the PERCEPTRON algorithm. Whoever is successful in like downloading that Octave and kind of getting it up can just simply run that, and you will see how the perceptron hyperplanes are moving and how we are using support vectors to kind of find the optimal hyperplane.
Okay.
Yeah. That's it. Nitish, you want to add anything?
No, I think that's good.
Okay.
That's pretty good.
Yep. That's it. Thank you.
Thank you.
Bye.
Bye.